Howdy, folks. Our goal today is to derive an expression for um, the electric field made by a disk of area density sigma, and we're going to find that field along the central axis of that disk, and we're going to employ something that we've developed so far already, which is the electric field made by a hollow ring or a disk of, or sorry, a hoop of charge of linear density lambda, right? Um, so, bottom line is we're integrating all these dx's because of the symmetry of the vertical symmetry about this axis. And, well, that's dE cos theta, and here's dE cos theta, and the cos theta is an x over r. And, well, when you get to the actual integral right here, well, there's a constant. X is a constant, R is a constant, and all you have to do is integrate, just literally integral dq, and that's just q. All right, so, and then of course, not of course, but r cubed turns into our little r is x squared plus r squared to the 1/2, but that's cubed, so there's your 3/2. Okay, so, well, we're going to use this result here. All right, because what we can say is that this disk is made of lots of little concentric hoops. All right, each of which, for me, has a radius r, like we said here, and, well, has a thickness, a little tiny thickness, dr. All right, and so we're actually saying that hoop is my elemental unit. So when I say, well, if I say that this whole disk has an area density charge per unit area, then, well, the charge of that little, well, of any area is sigma times A. The tiny little charge of a tiny little area is sigma times that area. And then my little area of my little element, right, is dq is sigma. The little tiny area is the length of that, well, the circumference of that hoop times its little tiny thickness. So that's 2 pi r dr. Okay? So, when we are going to evaluate or set up our integral for E at this point P along the x-axis, what we're going to say is we're going to add up all the elemental units of field made by each ring. And when I say add up, I mean integrate. Okay? And that means that we're going to say that each little ring has, well, let's see, that's a k. I will say, right, let's just refresher, E of a ring is k, q, x over x squared, for me, r squared to the 3/2. All right, so when we're saying our dE ring is just k dq x over x squared plus r squared to the 3/2. Well, my variable here is r. Our r's are going to vary from a radius of 0 to a radius of capital Y. And, well, luckily, we have a way to express dq in terms of dr. So that's good. So we sub in, we say that E is k, here's my x, here's my dq, 2, whoops, I always forget that sigma. Sigma 2 pi r x squared plus r squared to the 3/2 dr, where r ranges from 0 to y. All right, now, you probably, it's, if you haven't done it already, not a bad time to take out some constants like k and sigma and pi. Now there's a 2, but I'm going to leave that in here. And I'm going to say this is 2. Oh, x is also a constant. 2r over x squared and r squared 3/2 dr. Okay. Now we are in a place where that's a doozy of an integral, but what you notice is we've got something where we have a function and the derivative of that function with respect to the variable we want to integrate over. So that's a great candidate for what we call a u substitution. All right, so I'm going to say let's let u equal that whole bottom thing, x squared plus r squared. All right, and then du dr is going to be, well, that's the x squared just goes away. It's just a number. And then we get 2r. All right, so therefore du is 2r dr. All right, so we can turn this integral, maybe I'll put this stuff off to the side a touch. That means that this integral can turn into, how about just this part? Turns into, let's see, well, I've got, in the bottom I have u to the 3/2. In the top, I've got du. Oh, good. That's not too bad. So that means this is really the integral of u to the negative 3/2 du. So that is, let's see, that is, you put this up one right to the negative 1/2 and times negative 1/2. Oops. Yeah. Now, what's u? Right? Well, u is x squared plus r squared. So our integral, this part, turns into negative 1 over 2 x squared plus r squared to the 1/2. Except this is supposed to be a plain old 2. Yeah. A plain old 2. I just integrated wrong. Okay, so now, right, we put this stuff in here, but let's carry all our constants down. So now we have that our E is, okay, sigma pi x times, well, here's the 2, here's the negative, here's the x squared plus r squared to the 1/2. And remember, now we still have to evaluate from 0 to our capital Y. All right? And, okay. So this goes, well, negative k by, got a 2 in front. Negative 2 with an x times, let's see, that's 1 over x squared plus y squared to the 1/2 minus 1 over x squared, well, because the r is now 0, x squared to the 1/2 is x. Yeah? And let's see. I'm going to put this x through both. We got negative 2k sigma pi x over x squared plus y squared to the 1/2 minus 1. Well, and then we'll handle this by saying 2k sigma pi 1 minus x over x squared plus y squared to the 1/2. Yeah? Okay, I mean, you can be done. This is E. Lots of times we'll express K as 1 over 4 pi epsilon naught, right? That gives us 2 sigma pi over 4 pi epsilon naught times all this stuff. 1 minus x over x squared plus y squared to the 1/2. And then we say bye-bye, and then we say bye-bye, okay. E is, now we're getting to a place that we like. 1 minus, okay, fine. Okay, so what we can check? What can we check? All right, we can check if x gets really big, right? So if x is way bigger than y, well, then this term approaches, well, x squared plus y squared is really approximately x squared. And then we have x squared to the 1/2, so we get 1 minus x over x. We get 1 minus 1. We get 0, and when we're really, really big x, yeah, the field should be approximately 0. Or should get to be 0. Okay? We also have, let's see, we also have the case where, all right, if x is really small, if x is way smaller than y, that means that we're really close to this disk, right? Really close to the disk. Well, really close to the disk, then we get, let's see, if x is really small. That's not by 1, is it? That's really small. Oh yeah, sure, that's fine. Yeah, if x is really small, really, I guess we're saying as x approaches 0, it's kind of like saying as y gets way bigger than x. Well, as x approaches 0, then that term approaches 0, and then the whole term in here just is 1, and what we get is this. The E is sigma over 2 pi epsilon naught, and that's just a constant. Sigma is a constant. Epsilon naught is a constant. And when we're really, really close to this disk, well, the field lines don't diverge yet. So the field's pretty darn constant. Okay, so a couple things check out well. You know, this is a pretty standard expression for that field near a charged disk. All right, that U sub is a great little bit of practice there. You know, nice that we can simplify down to, you know, a pretty nice little constant out in the front, and then some variability in the inside of those brackets. All right, but we're home free. All right, folks. Thanks.